Hello everyone, this is Zhongcheng Ma from Havula University of Applied Science speaking. I'm the principal research scientist in HamTech Research Unit. The title of my presentation is FE Model Validation and the Advanced Analysis of Steel Members with Steel Cladding at Elevated Temperature. The presentation is divided into 4 main sessions: Introduction, FE Model Validation, Advanced Structure Analysis, and Conclusion. I will first go to the introduction session. This is a one-story industrial steel frame building with steel cladding. Typically, in Finland, the sandwich panels are used as wall cladding and trapezoidal sheeting plus insulation as roof cladding. The system is subjected to vertical snow load and horizontal wind load. Recent research has shown that the steel cladding system is capable of providing in-plane support to column against minor axis buckling and therefore increase the buckling resistance at normal temperature. This was a research topic in previous work by Easier Project and Hedman Peterson in her dissertation. What about in case of fire? Are there stabilization effects for individual members and the entire building against wind and catenary actions from snow load? We answer the first research question in this presentation and the second question in another presentation. The project consists of 9 work packages. Work package 2 to 4 are the testing part and 5 to 6 are the firm simulation part. Work package 5 is regarding the simulation of tests, and work package 6 is the simulation of the entire building, which includes the stabilization of individual member at elevated temperature and the entire building in fire. Task 3 is regarding the stabilization of individual member at elevated temperature, and the research results are presented in this paper. This slide shows 9 partners in this project. Temple University of Technology, now the Temple University, is a coordinator. HAMC is a work package leader of work package 6. Now let's move to the second session, FE model validation. Left picture gives an overall view of the test arrangement. The specimen consists of 3 steel columns, and the sandwich panel are connected with the steel column using self-drilling screws. The compression forces are applied to the central column by 2 cylinders using a load distributing element. Additional uniform bending moment is applied by a separate cylinder with a specified eccentricity. Inner face of sandwich panel and central column are heated using electric padding. The eccentric load is set as 10% of the actual load, and the eccentricity is about 75 centimeters. 2 model structure has been simulated. Left picture shows a firm model for steel beams with trapezoidal sheeting, cladding, and the mechanical property of short nail at elevated temperature. The right pictures shows the sandwich panel cladding and the mechanical property of the self-drilling screws at elevated temperature. This is a load displacement curves for trapezoidal sheeting cases. Left is the normal temperature and right is 300 degrees. At the time of simulation, we only know that the steel column has a grade of S355. Therefore, 2 yield strengths has been used in the simulation 410 and 450 megapascal. That's typical value for S355. The actual measured yield strength is 460 megapascal in the flange in the later tensile coupling test. For sandwich panel cladding, the simulated peak load is 7% lower than the test at 20 degrees and 12% higher at 300 degrees. The simulation agreed well with the test for elastic stiffness. The effect of geometrical imperfection and residual stress is further investigated. The dotted curve in the right picture shows a load displacement curve with imperfections. The peak load is around 5 to 6% lower with the specified imperfections. Next, we will go to the advanced structure file analysis session. Let's take a look at the resistance capacity of the compression member at elevated temperature. Here are two columns connected by sandwich panels subject to actual load. The stabilization at ambient temperature has been studied by Hetman Peterson. The FE model developed by the author has been validated, and both geometrical imperfection and residual stress are included in the firm model. The analysis at phi has been performed to investigate the load-bearing capacity. Here are the results. The leftmost column is the ISO phi expression tile. There are specific temperature profile corresponding to each phi exposure time. Rightmost column is the load-bearing capacity of column without sandwich cladding. In the case of no delamination is taken into account, the load-carrying capacity of the steel column is twice as the case without cladding. With delamination is considered, the load-bearing capacity increased 25% to 100% due to the presence of sandwich cladding. Two types of steel cladding, Lugi T153 trapezoidal sheet and Lugi sandwich panel has been investigated. A common beam column with both actual load and bending moment. Load ratio is about 0.28. Geometrical imperfection in minor axis is taken into account. And the delamination of inner steel face from a mineral wool core after 300 degrees is also taken into account in the analysis. The left graph illustrates the actual load. Lateral displacement curve of steel column for sheeting cladding. Upper dark curves are for the case with the steel cladding is connected with the tensile flange of the steel column. Lower green curves are for the case when sheet cladding is connected with the compression flange. It can be seen that the steel cladding increases the fire resistance when connected with the compression flange. No significant change in the fire resistance otherwise. The fire resistant behavior of steel member is different when the steel cladding is connected with the column at tension flange and compression flange. For T153 cladding at tension flange of steel member, the increase is insignificant, around 0 to 8%. For cladding at compression flange, the increase is around 11 to 13%. In case of spar 230 sandwich cladding, at tension flange, no increase in fire resistance for both with and without fire protection. At compression flange, there is slight decrease due to the presence of sandwich cladding. This reduction is around 3%. Now conclusions. For the column and the axial compression, the load carrying capacity due to sandwich cladding increased 25 to 103% at elevated temperature. For trapezoidal sheet cladding, the increase of fire resistance is around 11 to 13% when cladding is connected with the compression flange. Insignificant change in the fire resistance of sandwich cladding for beam column. The financial support from Step Fee research project by Research Fund for Coal and Steel and FESFS research project by Finnish Fire Protection Fund are greatly acknowledged. This is a reference. Thank you for your attention.